Hello again, dear students. Today we move on to the part 2 of our discussion for quarter 2, week 3 in Mathematics 7, which is the introduction to algebra. Here is our most essential learning competency as well as our reference. And let us start with defining what an algebraic expression is. So an algebraic expression are combinations of variables, numbers, or at least one arithmetic operation. When we say arithmetic operation, those are, or that includes addition, subtraction, multiplication, and division. So here is an example of an algebraic expression. We have 3x plus 5y minus 10. That expression has the following terms. We have 3x, 5y, and 10. These terms are separated by the operations addition and subtraction. So if I'm going to ask you how many terms are there in this algebraic expression, so your answer should be 3 because we have 1, 2, and 3 terms. Another one, 3 and 5 are called numerical coefficients. So we have number 3 here and number 5. Later on, we will define those terms. Then x and y are called literal coefficients of variables. We have here the x and the y. And lastly, negative 10 is called a constant. Let's go over to the definition of terms. So the first one is the word term. It is either a single number or variable or numbers and variables multiplied together. For example, in number 1, we have the algebraic expression x squared plus 3y plus 5. The terms are again separated by either addition or subtraction. So we have the first term, which is x squared, and then we have 3y, and then the term 5. This expression has 3 terms. For example, number 2, in the expression negative 5y cubed plus 2xy minus 4, the terms are negative 5y cubed. So we consider the sign, which is negative. The second term is 2xy, and the last term is negative 4. Since it follows the operation minus, it means that it carries the sign which is negative. We also have to take note of the term literal coefficient, which is a variable including its exponent. We use the same examples that we've used a while ago. And we have x squared plus 3y plus 5. The literal coefficient of this term is x squared, so we have to include its exponent, which is 2. And the literal coefficient of this term is y, while for this last term, it has no literal coefficient. So our literal coefficients are only x squared and y. For example, number 2, we have the expression negative 5y cubed plus 2xy minus 4. The literal coefficient of this term is y cubed. This term, its literal coefficient is xy, and for the last term, it has no literal coefficient. Number 3, we have the term variable. It is a symbol for unknown numbers. It is usually a letter like x or y, or in our first examples, we used the letter n, but again, you can use any letter. Next, we have the term numerical coefficient. It is a constant multiplier of the variables in a term. So in this example, our numerical coefficient can be identified per term. So for the first term, our numerical coefficient is 1. How did we get 1? Since we don't have any number there, it means that that is 1 times x squared. Okay, its numerical multiplier is 1, so that is its numerical coefficient. For the second term, our multiplier or numerical coefficient is 3. And then for the last term, we have the numerical coefficient 5. Here is another example. So we have negative 5y cubed plus 2xy minus 4. The numerical coefficient for the first term is negative 5. For the second term, it is positive 2. And for the last term, we have negative 4. Again, we include its negative sign. Next, we have the word constant. It is a symbol which has a fixed numerical value, so it doesn't change. For example, in the expression x squared plus 3y plus 5, the constant there is number 5, since 5 will always be the same even if the value of these two terms changes. The same with number 2, our constant is the third term, which is negative 4. So negative 4 will always be negative 4. It doesn't change in value. Next, we have the degree of each term. It refers to the sum of the exponents of the literal coefficient. For example, in number 1, if we have the literal coefficient x squared, since its exponent is 2, it means that the degree of this is 2. And for 3y, the degree of this is 1. Why? Because y has an exponent of 1, which we do not put anymore. We just write it as 3y, but it has an exponent which is 1. Okay, so the degree of this term is 1, while the degree of this term is 2. For number 2, in negative 5y cubed, the degree is 3, since the exponent of our literal coefficient is 3. For this one, its degree is 2. How did we get 2? Because the exponent of x is 1 and the exponent of y is 1. Since they are together, they are only one term, we have to add its exponents. So 1 plus 1 is equal to 2, which makes its degree 2. And for negative 4, its degree is 0. Why? Because it doesn't have a literal coefficient. It doesn't have a literal coefficient, so its degree is 0. Here is an example, a table with examples. For the first example, we have the expression 3x plus 4. The terms there are 3x and 4. So it has two terms. Next, the literal coefficient is x. We only have x as the literal coefficient. The variable is x again. The numerical coefficients are 3 and 4, while the constant is 4. The highest degree is 1, since the exponent of our literal coefficient here is 1. For example, number 2, we have the expression 2m squared minus 5m minus 2. We first look at the terms. So the first term is 2m squared. So that should be 2m raised to 2. And then the second term is negative 5m. And then we have the third term, negative 2. Again, take note that we have to include if it is negative or positive. Okay, if it follows the minus operation or the subtraction operation, so we have to write that as negative, the term as negative. For the literal coefficients, the literal coefficient for the first term is m squared. For the second term, it is m. And we only have one variable used in this expression, which is letter m. For the numerical coefficients, we have 2, negative 5, and negative 2. The constant is the last term, which is -2, and the highest degree that we have is 2. That's why it is our highest degree. Go over the other examples. So here is example number 3. Example number 4. For example number 3, its degree is 3. How did we get that? For the literal coefficient, we have x squared y. Okay, that is our first literal coefficient. The exponent of x is 2. The exponent of y is 1. We have to add those two. So 2 plus 1 is equal to 3. That's why the highest degree for this expression is 3. Next, for example 4, 6m cubed. Okay, so its literal coefficient for the first term is m cubed. That is already our highest degree. That's why the degree of this expression is 3. And for the last one, we have a raised to 7 plus 2a raised to 4 minus 6a plus 2. We have the degree of 7, since our first literal coefficient here is a raised to 7. Okay? Now, we also have the term polynomial. It comes from the word poly, meaning many, and nomial, meaning terms. A polynomial contains 2 or more algebraic terms. It is an algebraic expression that represents a sum of 1 or more terms containing whole number expression on the variables. Again, it contains whole number expression on the variables. For an algebraic expression is not a polynomial if the exponent of the variable is not a whole number. So if the exponent is not a whole number, for example, it is a fraction or an irrational number, we do not consider that as a polynomial. As well as if it is a negative exponent. So that is not a polynomial. For number 2, an expression is not a polynomial if the variable is inside the radical sign. Again, if the variable is inside the radical sign. And for the third factor, which makes an algebraic expression not a polynomial, is that if the variable is in the denominator. Okay. Here are examples of polynomials. For number 1, 4x squared is a polynomial since the degree of the term is a positive integer. Number 2, we have here a polynomial with 2 terms, and the degrees are both positive or whole numbers. For number 3, it is also a polynomial because the only number inside the radical sign is 43, while x is outside. Okay, it is not included inside the radical sign. But for number 4, it is not a polynomial because our variable x is inside the radical sign. And for number 5, we have the expression -7y raised to -3 plus 6y squared minus 12, which makes it not a polynomial because in our conditions a while ago, it is not a polynomial if the exponent of the variable is a negative number. So it should be a positive integer. Okay? 1, 2, and 3 are polynomials, but 4 and 5 are not polynomials. But still, they are considered algebraic expressions. And here are the types of polynomials. First, according to number of terms, we can classify it as monomial, binomial, or trinomial. For monomial, comes from the word mono, which means 1. So if you count the terms and there is only one term, you call that as a monomial. Here is an example: 3x, -10, 6xy. As for binomial, by, which means from the prefix by, which means 2, it means that it has two terms. Okay, here are examples. 2x plus 4y. Our first term is 2x. The second term is 4y. The next one is x to the fourth power minus 3xy. Our first term is x to the fourth power, and the second term is negative 3xy. Okay, negative 3xy. For the third example, we have xy squared plus 6x, so it has two terms as well. And the third classification is trinomial, from the word prefix tri, which means 3. Okay. Examples, we have x to the fourth power plus 3x squared minus 3. We have the first term, second term, and third term. And again, it is separated by addition or subtraction. Here is another example. We have 3y to the fifth power minus 3xy minus 18. And lastly, we have x cubed plus 12x squared plus 9. Now, we can also classify polynomials according to the degree. We've learned about degree a while ago. It refers to the highest exponent of our literal coefficients. Okay, the first classification is a constant, wherein the polynomial is of a degree 0. Linear if the degree is 1. Quadratic if the degree is 2. Cubic if the degree is 3. Quartic if the degree is 4. Quintic if the polynomial has a degree of 5. And the next degrees have no universal name yet, so they are just called polynomial of degree 6, 7, 8, 9, and so on. So you identify it as a polynomial of degree 6, 7, and up. Okay. Here are some examples of polynomials with its degree. For the first polynomial, we have 3y to the fifth power minus 3xy minus 18. The degree of our first term is 5. It means that we classify that as a quintic polynomial. For example number 2, we have negative 2x squared y squared plus 3x minus 10. For our first term, we have the literal coefficient 2x squared y squared. We have to add its exponents 2 and 2. The sum is 4. That's why this is a quartic polynomial. The third example, 7a squared. The exponent of the literal coefficient is 2. So our example, or this example, is a quadratic. And for the last one, xy to the third, or xy cubed plus y squared minus 5x squared minus 11. The exponent of this x is 1 and the exponent of y is 3. Since there are only one term, we have to add 1 plus 3 and the sum is 4. Again, this is an example of a quartic polynomial based on the degree. Now, take note that the standard form of polynomial means that the terms are arranged from highest degree to lowest degree. In a polynomial, the leading coefficient is the term with the highest exponent, and leading coefficient is the numerical coefficient of the leading term. Let's look at the table for the examples on how to write polynomials in standard form, as well as identifying its leading term, leading coefficient, degree, type of polynomial according to number of terms, and its classifications according to the degree. For the first example, we have the expression negative 4k squared L plus 3k plus 9L minus 5. The degree of the first term is 3 because we have 4k squared L adding 2 and 1, which is the exponent of L. 2 plus 1 is equal to 3. That's why our degree is 3, which makes it a cubic polynomial. Counting the number of terms, we have 1, 2, 3, and 4. It has 4 terms, which makes it a polynomial based on the number of terms. And let's continue with writing the standard form. The first term is then negative 4k squared L because its degree is 3, followed by 3k with the degree 1 and 9L with the degree 1 as well. We can write 3k and 9L in any order, but since letter k comes first, so we write 3k first. And then followed by 9L minus the constant 5. Having that, we can write the leading term, negative 4k squared L. From that, we can take the leading coefficient, which is negative 4. Next, our next example is negative 3 plus 10x squared. Negative 3 is a constant, having the degree of 0. And the degree of our second term is 2, because the exponent of the literal coefficient is 2. That means that 10x squared should come first in order for us to write it in standard form. So 10x squared minus 3 is the standard form. From that, we take the first or the leading term, which is 10x squared, and then the leading coefficient is 10, while the degree of our literal coefficient is again 2. That's why the degree is 2, classifying it as a quadratic polynomial. And since it has 2 terms, so we call it a binomial. Next, for the third example, we have 13a to the 5th power. It has only 1 term, so we call it a monomial. And it is already written in standard form because there is only 1 term. It is also the leading term, and the leading coefficient is 13. The degree of our literal coefficient is 5, so we call it a quintic polynomial. Lastly, we have 5x plus 7x minus 8x cubed plus 1. From that, we can identify 8x cubed or negative 8x cubed as the leading coefficient because its exponent or the exponent of the literal coefficient is 3. The next term is 7x squared with 2 as the exponent or the degree, and then followed by negative 5x followed by plus 1. And then the leading term is then negative 8x cubed. Our leading coefficient is negative 8. The exponent of our literal coefficient is 3, which makes it a cubic polynomial. And the expression has 4 terms, so it is considered a polynomial. I hope that with those examples, you were able to identify and differentiate the different terms in algebra, which we will use in our next discussions. So prepare, because our next lesson will be on evaluating algebraic expressions. Until next time, bye!